G'day viewers. In this segment I'm going to talk about shortest path routing for selecting good paths through the network. So in previous segments I've talked a fair bit about what a good path through the network, or that routing is going to find the best path through the network, but we haven't really said what that means. In this segment we're going to delve into that topic and provide an answer. And the answer we're going to provide is going to assign costs to links and use the notion of shortest paths as a way of defining what a good path is. Let me go into that in a little more detail. So we would like routing to find best paths or good paths. Well, what are they? It really depends on what you, the network operator, want. And there are many different possibilities here. You might want a good path to have low latency because this would avoid a circuitous route. There's no need to sort of go from the west coast to the east coast and back if you could avoid it. On the other hand, if you had a different kind of network, we might want paths which had high bandwidth. You might want to avoid any kind of slow or low bandwidth links because this way you would fit more traffic through your network. Depending on exactly how you paid for your network too, you might want to avoid expensive links. Maybe you'd want to avoid cellular links of some kind, for instance, just because you had some budget on them and you were going to have to pay a lot of money if you used them too much. Or you might want to minimize the number of hops that packets went through the network, because in some way that would reduce the volume of switching that goes on, and if you're lucky, maybe some of your equipment. And these are all different possibilities. Now, there's actually, while it might seem like I've admitted pretty much everything here, there's a class of best that we've actually ruled out here that I haven't mentioned. And that is to do with hotspots. Now, it might be the case that just in this network there's a bit of a hotspot at B, and if we've sent traffic from A to E along that blue path there that's shown in the network here, like this path, then maybe we would say, hey, there's already a lot of traffic at B, so we don't want to send traffic from G, say, to C. We would like other traffic to go round instead of through B. Well, we're not going to focus on those kind of policies today because that kind of routing involves the traffic. And best, as we're going to define it now, will only consider static features of the topology, such as what nodes are connected where. You might also see that I'm going to represent networks as these kind of graphs. So in this diagram here, a line here, this is a link, and the circle here, this is a node. Previously I had a little icon or a picture for some of these things, but often for routing it'll suffice just to call it a dot and give it a label like a name, like A through G. Okay, so best could be all of these things. This is a little bit too complicated. What can we do? With shortest paths we come up with an approximation which can represent many of these factors roughly. And what we will do is make a cost function so that we'll be able to compute the cost of different paths, and we'll choose the path which has the lowest total cost to be the best path. By assigning the costs in different ways, we'll be able to capture some of these different factors. Now, often we'll call the lowest cost path the shortest path. This is what you would get if you assigned the cost function to be the distance. And since this is a common choice in large ISP networks, what I will tend to do is I'll be a little sloppy, and I'll use cost or distance interchangeably, and we'll also use lowest or shortest interchangeably, so don't be too confused about that. The way shortest paths will work is we'll go through these three steps. First of all, we will assign to every link a cost or a distance, and we'll do that to capture the factors we care about. It's literally distance if we wanted to minimize the latency through the network. If you made it all 1, you would minimize the hops through the network if every link was 1. If you cared about bandwidth, you might assign fast links low costs and slow links higher costs, because that way if we take the lowest cost, we'll tend to prefer the faster links. At any rate, you assign a cost to a link, and the operator does this. This is policy. And then we simply define the best path through the network between every pair of nodes as the path through the network that has lowest total cost or is shortest. And if we turn up any ties in that process and a couple of different paths have an equal cost, then we're just going to randomly break those ties and pick a path Whatever we pick out of those ones, it will, since it will have lowest cost, it'll be good. It will be best according to our definition. Well, let's see some examples to see how shortest paths work. Here I have a picture on the right of a fairly complicated looking network topology. It's that graph from before where the lines represent links and the nodes represent different equipment kinds of icons. And what you can see I've added here is I've added a number on every link. This is the cost of using the link which I've assigned. In this diagram, all of the links are bidirectional and they have the same cost in either direction. It's possible to extend all of these models to networks that have links which are not bidirectional and which have unequal costs in either direction, even when they are bidirectional. But we're going to ignore all of this, and in the networks we'll look at, we'll have bidirectional links with equal costs. Okay, so the task here is to find the shortest path from node A to node E through this network. What's it going to be? In this segment, we're going to solve problems like this simply by inspection, and later we'll see algorithms which will work this out. Now, just looking at this network, I see different possibilities here. I mean, there's a node directly here from A to E. That could be good. That has cost 10. Well, actually, I can see I can do a little better than that if I go through here. If I go A, B, E, that has cost 8. That's lower, so it's a shorter path. It's best. Is this the shortest possible path? Well, you should have a look at for a moment and see if you can come up with anything better. There is actually a better path through this network. Hopefully you've worked it out, and now I'm going to draw it in for you. It's this path, A to B, B to C, and C to E. That has cost 4 plus 2 plus 1 is 7, and that's the shortest path on this graph. I've cleaned up this diagram a little bit and retraced it over, and you can see it there. And I've also listed just the costs or the distance function for some other paths that you might think of. Here was our AE, that was 10. We also discarded ABE is 8. We did slightly better than that. You might also come up with some other paths just looking around, but they'll turn out not to be better. For instance, ABFE, this path, has cost 9. No, not quite so good. Or you could imagine doing something going a little further around looking for something better. ABCDE costs 10. Nope, and everything else is getting longer. So the other one is definitely the shortest path. So now we know what a shortest path is. The interesting thing about these shortest paths, which we're going to use as part of our routing algorithms to compute these things, is that the paths have what's called an optimality property. And the optimality property is that if you have a shortest path, any subpath of it is also a shortest path. That's kind of handy, actually. So in one shortest path, there are actually many different shortest path segments we found. So for instance, our path ABCE is the shortest path. Okay, well that means I actually found a lot of other shortest paths. AC is the shortest path, sorry, ABC, that first segment. CE is the shortest path. BCE is also a shortest path, and so on. Now, you can actually reason fairly easily to see why these must be shortest paths. The reason, for instance, that BCE is the shortest path, if ABCE is the shortest path, is imagine for the moment that I could find a better path than BCE. Well, if that was the case, I would simply use a different route to reach E by taking that path and stapling the A to B bit on front of it. And then I would have a better path from A to E. But we know that the path from A to E we have is the shortest, so it's not possible to do this. It's a contradiction. So that means that the path from B, C, and E must itself be a shortest path. There's also another nice property we get with some of these shortest paths. And this should give you a nice warm feeling. You should be beginning to see why, in fact, we work with shortest paths, because they can approximate some of these different cost factors, and they have a lot of attractive properties. So the other interesting property is that if I take the union of all of the different shortest paths from all nodes to a particular destination, then I will get what's called the sync tree. It will actually be a tree, because once you go further in, then the path, when two paths meet, they will both follow the same route from there on to the destination because of this optimality property. So let's see if we can find the sync tree for E. So that's all destinations going towards E. You can also similarly, in our formulation, find source trees, which would be all of the paths from one node, say E again, out to all other nodes. In fact, given that we're looking at bidirectional links with equal cost, the sync tree and the source tree will basically be the same. They'll just be pointing in different directions to go towards the root or away from the root. And I'll use them a little interchangeably too, depending on what is most convenient. So let's find the sync tree for E. Well, C goes towards E, so we had this link here. Now I can see the shortest way to get from D to E is just to go along this link, so that will be part of the sync tree. From F to E, the shortest way is along this link. There's no other shorter way around. It's not always the case that the direct link is shortest, by the way. From B to E, we actually saw that, we want to go to C, and then from C up to E, a dogleg way, rather than going along that direct link BE. Well, what's left? Can all of the nodes get to E yet? Not quite. I need to extend it. We need to work out how H gets to E. Well, it's going to have to go along here to C, and then from C, it's going to go straight up to E. And G also is going to have to decide which way to go. I can see cost 3, 6 here, or I can also see cost 6 up here. That's a tie, and we could choose either of these, and I'm somewhat arbitrarily going to go like this. So this is a sync tree for E, and since we broke a tie, there could be more than one. Let's just clear that up. So there are some very nice implications of sync trees. Because of this shortest path property. Given that we have these shortest paths, all we need to follow them towards a destination is the destination. The source that they came from is irrelevant. So you can see here once I get to node C, I'm going to then go onwards to E. It doesn't matter whether the packet came from H, or whether it came from B, or whether it actually came from A. Once it gets to C, it simply follows the same remainder route to E, and so all we need to do is look at the destination. That's fairly simple. What's more, each node only needs to work out the next hop to send it to. In this graph, we can sort of see how we might send the whole path, but really all A needs to know, for instance, is that it needs to send it to B, rather than directly to E, and then someone else like B will carry it further onwards. This leads to a notion of a forwarding table for a node. We assumed that there were forwarding tables to do IP forwarding. At a node, the forwarding table is going to list the next hop for every single destination. So that's going to allow us to forward a packet because we'll know the direction to send it in by simply looking at the destination. You can see this will fit well with shortest path routes. It may be that if we compute shortest path routes, we will actually know a lot more about the routes through the network than simply the next hop. As I was saying, in this diagram, we know the whole path that you're going to take from a node to the destination. But we're not going to need that for forwarding, and so we might distill a forwarding table out of the routing table and ignore information we have. So far, we've just been using inspection to look at these graphs and find out which way to go with the sync trees. In the next segments, we'll look at how you can compute these paths yourself, or rather the nodes can compute it themselves by using well-defined algorithms.